This video discusses directors and activators and deactivators and how they influence the functionalization of benzene rings. We have three categories of molecules. The first are orthopara directors that are activators. And those are things like methoxy group. We're looking for molecules that have lone pairs directly attached to the atom that's on the aromatic ring, with the exception being the halogens, which are orthopara directors but deactivators because of the electron withdrawing nature of the halogens, giving a dipole pointed toward the halogen, so our ring is partially positively charged, giving us a less nucleophilic molecule. Then we have compounds that are metadirectors and deactivators, and those include compounds that have stronger electron withdrawing groups such as nitro. We'll see things like cyano, tetraalkyl ammonia, etc. I made a slide that shows the effects, the directing effect, as well as whether things are ortho or metadirectors. So everything in blue is an orthopara director, and the farther something is to the left, the more directing the effect is, and the more activating the group is. And the only exception in this row is the halogens, which are deactivating, yet they're still orthopara directing. So again, everything in blue is an orthopara director. And even in red over here, it's still an orthopara director, but a deactivator. Then we get down to the groups in red, and these are metadirectors, and their directing effect is then proportional to this, or it falls in line with this this red line that I've shown here. So everything that's under the red line is a metadirector and also a deactivator. So become familiar with these groups, because that will help you when you're functionalizing benzene rings to know whether to put something ortho, meta, or para, and also whether forceful conditions are needed for a transformation to occur, or if it will occur at all. What happens when you have multiple substituents and you have to figure out where to put the next functional group? For example, if you have this compound, methoxynitrobenzene, then we have the methoxy group that is an ortho para-director, and the nitro group, which is a meta-director. Then what we want to do here is give the ribbon, or award the trophy, to the most activating group. And the most activating group here is methoxy, and we know that because nitro groups are deactivating. So in our products, we're going to see chlorine at the 2 ortho positions as well as the para position to the methoxy group, although we should note that this product in the middle is probably minor because of steric effects of being between the methoxy and the nitro groups. What about when we have a methoxy versus a methyl group? Here we have an electron donating group and an electron donating group. How do we know which one to choose as our preference? What we want to choose is the one that is more electron donating, which is our methoxy group. So here this is our ortho para director, so these 2 positions are going to be the ones that are functionalized, giving us our bromine at the position ortho to the methoxy group. Then in our last example, we have a chlorine versus a nitro group, and here we've got chlorine, which is ortho para directing, and our nitro group, which is also ortho para directing. So in this case, both groups win, but it's not because of the nitro group being meta directing. The nitro group is deactivating, so this position is all coming from the chlorine atom being an activating group. So let's do some practice and predict the positions that will undergo substitution. So I want you to pause your video and see where you think the positions of functionalization will go. So in our first example, we are comparing a methyl group, which is ortho-para-directing, to our nitro group, which is meta-directing. So both of these positions want to be functionalized at the same position, although keep in mind it's that methyl group that is winning. So it's because that is the activating group. So we'll have our substituents going ortho and para to the methyl group. When we look at the next example, we've got our alkyl groups, which are ortho-para directing, and then our carbonyl groups are meta-directing, and the meta position to the carbonyl is blocked, so the only position of functionalization here is this one. Next, let's compare our methyl group to our nitro groups. Our methyl group is ortho-para directing, and our nitro groups are meta-directing. And notice that meta to the nitro groups are each other. They're both meta to each other, and they're meta to the methyl group. So there's not going to be any directionality afforded by the nitro groups, and anyway, the methyl group wins in direction. So we're going to get functionalization at all three of these positions. And in the last example, I put together a biphenyl ring, because remember that if you look at that slide a few slides ago where I showed you what substituents were ortho-para directing, that phenyl is one of those. It's an electron donor. It's got pi bonds that are next to the benzene ring. So what we're going to see here is that we've got the methyl group doing ortho-meta directing and the phenyl group doing ortho-meta-para directing. So any of these positions can be functionalized, but based on sterics and electronics, this one is going to be the one that wins. That's para to the toluene group. Steric effects also play a role in the position of substituents that are incorporated in reactions. For example, if you compare isopropyl methylbenzene and think about where is the functionality going to go, we know that the ortho groups to isopropyl are activated and the ortho groups to the methyl group are activated, so all four positions are electronically activated. But it turns out that the compound with the bromine ortho to the methyl group is going to win as the major product because the methyl group is less sterically hindered. When we compare these isopropyl and methyl groups that are at the ortho positions, they're meta to each other, then we have these three positions activated, and that's indeed where we see two of our products where we have a nitro group that is close to the methyl group, and then another one that's close to the isopropyl group, but this one is minor because the isopropyl group is bigger. And then this one on the right where we've got a nitro group between the isopropyl and the methyl groups is not observed at all. Blocking groups are pretty interesting. They're kind of like a protecting group in that they can be introduced into an aromatic ring and then removed at a later step. Recall that with the sulfonate group, it's installed with fuming sulfuric acid, which is sulfuric acid plus SO3 gas, and that it can be removed in dilute sulfuric acid. So we can use this to our advantage in directing substituents. So what if we want to make this compound, isopropyl chlorobenzene? We know that if we treat isopropyl benzene with chlorine and aluminum trichloride, that we get this product as major, where the chlorine is para to the isopropyl group, and that's because of electronic effects and steric effects. Electronically, we can still put a chlorine ortho to the isopropyl group, but because of sterics, it's not going to go there. So what we need to do is install a blocking group para to the isopropyl group. So we'll put this SO3 group para to the isopropyl group using fuming sulfuric acid. Then we'll use aluminum chloride and chlorine to functionalize the aromatic ring, and then we use dilute sulfuric acid to take away the sulfonate group. So again, we're using fuming sulfuric acid to install the sulfonate, aluminum chloride and chlorine to chlorinate the molecule ortho to the isopropyl group, and then taking the sulfonate group away with sulfuric acid, dilute sulfuric acid. So at the end of this section, section 18.12, you get a reaction map of all the reactions that you know, but it's not a thorough reaction map. It stops at the aromatic functionalization, basically giving you about, I think, maybe all of these compounds in green. But I wanted to make the map larger to show you all of the things that you can do with functionalized aromatic rings to remind you that, for example, when you get to a carboxylic acid after you oxidize an alkylated aromatic, don't forget that you can treat that with lithium aluminum hydride, you can turn it into an ester, you can turn the reduced alcohol into an ether. There are all sorts of things you can do. So it's great practice when you're studying to make reaction maps like this and think of all of the things that you know how to do, because probably I've left some of them out of this map. Now we're going to spend our last slides doing some practice synthesis. So I want you to pause your video and think about how you would accomplish the following transformation, and then when you restart it, we will review the correct answer. So here what we want to do is consider how we're going to install our alkyl group. Before we get to the alkene, we've got to put our alkyl group on. And here we want to think about Friedel-Crafts alkylations and acylations. And we know that a Friedel-Crafts alkylation is not the right way to go because our carbon is primary. And if we were to do a synthesis with 1-chlorobutane and aluminum chloride, we would get carbocation rearrangement, or we'd get a hydride shift, and we would end up with the product as the sec-butyl instead of the N-butyl. So we don't want to use a Friedel-Crafts alkylation. Rather, we want to install those carbons by doing a Friedel-Crafts acylation. And now we have to figure out what to do with that carbonyl. Well, what we want to do with that carbonyl is get rid of it completely so that we can, because we don't have any oxygens in the product, and we're not going to do a reduction with the, we're not going to do a Grignard or anything. We don't need to add any more carbons. So we're going to use the zinc mercury amalgam with hydrochloric acid to do a Clemmensen reduction to get to our butyl group. But now how do we install an alkene? Well, to install an alkene, we need to be able to do an elimination reaction. And to do an elimination reaction, we need to be able to do an E2 with a strong, bulky base. So what we want to do is install a bromine atom at that benzylic position, like so. And to do that, we can use NBS or bromine and light. So here's another example. I want you to pause your video and see if you can figure this one out. This one's not quite as tricky because we know that our bromine and our methyl groups are both ortho-directing, and that the methyl group is ortho-directing and activating, so we're going to be able to install the methyl group and the bromine atom and then introduce the nitro group without doing anything tricky. So let's do a Friedel-Crafts alkylation. Then when we introduce bromine, we're going to put the bromine para to the methyl group as our major product, noting that we'll get minor products with the bromine ortho to the methyl group. And then when we introduce the nitro group, that is going to go to the ortho position to the methyl group because it is activating. Therefore, it wins over the bromine, which is also ortho-para directing. Now, our last example is the hardest example. It takes the most steps, so I want you to spend a lot of time thinking about this one. We're going to have to employ some reactions from the past that we haven't been using in Chapter 18. Now here we've got to install some carbon atoms, and we have to figure out how to best install them. Should we put the methyl group there first, or should we try to introduce this ether? And I'll just go ahead and tell you that putting the methyl group on is the right way to go. It's the simplest functionality. And it's going to provide for the para position to be activated by some other functionality. And what you have to realize here is that you're introducing not only two carbon atoms, but also an ether. And whenever you see ethers, I want you to think about the possibility for doing an acid-base reaction with an alcohol. And then how would you get an alcohol on this position? So at some point along the way, we want to have this compound that we can, in one step, or two steps actually, sodium hydride and bromomethane, we can turn that into our ether. So how are we going to get to this alcohol? Well, keep in mind that we can get alcohols and add carbons using our Grignard reagents. So where's that Grignard reagent going to be? Well, it's actually going to be the toluene ring that is functionalized with magnesium bromide. So I didn't mean to write that just there. Let's do a conversion. Now I can treat this with magnesium and we make a Grignard reagent. And then we have to figure out what are we going to treat the Grignard with so that we get two carbons and an alcohol. Well, so we need an electrophile with two carbons. So that's going to be acetaldehyde. The Grignard's going to attack this aldehyde to form our alcohol. So we want to use the aldehyde as step 1, and then step 2 we need to neutralize our product to get the alcohol. So that's a pretty complicated synthesis. And if you can do syntheses that are this hard, you're going to be in great shape for the exam.